Okay. Hello, my name is Kim Hyung-gyu, and today I'll present you about the quantum SVM implementation. So there, okay. Can I get rid of this part here? Okay, I'll just keep going. So for this presentation, I have read these three papers. The first is titled Quantum Support Vector Machine for Big Data Classification by this Royce. And this, I think this is the first paper that suggests that there are some advantage in aspects of its performance if you're using the quantum computer by calculating quantum support vector machine variables. And these two papers are usually focused on the implementation and experimental realization. But I'm not really go on how these are physically implemented, but we'll deal with the simulator level circuits, which can be learned in Qiskit simulator. So those two papers propose the small toy models that only have two properties for each training data and test data for support vector machines. So I will show how this toy model works. They suggest in this paper here. So first, we have to know about what is HHL algorithm, which is the biggest part of the quantum SVM algorithm. It's simple, just a way of solving a system of linear equation in quantum computers. So HHL algorithm is known for its supremacy compared to the classical algorithm for solving a system of linear equation. So in classical algorithm, it has time complexity of O n scale, which is linearly proportional to input size. Otherwise, on the other hand, quantum algorithm, which is named HH algorithm, has log n scale of time scale and complexity, which is exponential improvements compared to classical algorithm. So the HH algorithm is the way of solving a linear system of linear equations on the quantum computer. As you can see, the linear equations here can be rewritten by form of the matrix and vectors like this. And if we just regard this coefficient matrix to quantum operator and these vectors to the quantum state like this, we can just see that it's nothing but a quantum operation on some specific quantum states. So here, if we want to know about the x states, we just multiply inverse of A matrix on both sides. So before we start what's going on in this HH algorithm, we first assume that the matrix A is always Hermitian. Then we can decompose the matrix by using spectral decomposition as follows. So here, due to the property of spectral decomposition, we can easily calculate the inverse of matrix A as just as follows. The only difference is the coefficients of the eigenvector Kepler eigenvectors coefficients are inverse of the lambda. And B also can be regarded as a linear combination of eigenvectors Ui with the coefficients of Bi. So if we put these things all together in here, is substituting the A inverse of matrix A and B, you can get this, you'll get this. So it's just nothing but the linear combination of eigenvectors with coefficients inverse of lambda I and Bi. So the problem is now changed. We have to induce the coefficients here. But how can we induce the coefficients of coefficients like this? So B can be simply induced by feeding the input as a state of B because it has its coefficients with its coefficients BI can be presented as a recombination of the eigenvectors. So, and lambda I can be induced by applying some user-defined unitary gate U as follows. So what unitary U is doing here is just apply the computational basis to 0, and it will rotate to some. It will just induce the have amplitude as denominator of lambda and some normalization constant C. So you have some freedom. You have a freedom of what to choose in normalization constant C, but you have to be careful. It doesn't exceed the minimum value of the eigenvalue lambda, because this is the normalization constant. It is the larger. If it is larger than denominator, it will violate the normalization condition. So this is about the lambda I. So again, if we put this two states together, we will get this expression. So what we want to get amplitudes is here. So the scheme is like this. So we already consider the state of ancillar qubit here is 1. The case of the ancillar qubit is 0 will be regarded simply because it doesn't have contain any useful information to us. So this is the first step of HHL algorithm. First, feed B as an input, and second, encode the eigenvalue lambda I to phase qubits using phase estimation. So you rotate ancillar qubit by referring encoded phase qubits and then finally uncompute them. So I will give you a numerical example. Before we start, please notice that the ratio of the exact solution has a ratio of 1 to 3. The result output of the HHL algorithm is also must have the amplitude, the ratio of amplitudes 1 to 3, and that means the HHL algorithm execution was successful. Okay, first is set B as an input. Like here, input will be fed like this, and second, encode the eigenvalue lambda I to phase qubits using phase estimation. So the unitary U used in this phase estimation algorithm is exponential to IAT, which is the coefficients matrix. And so eigenvalues will be encoded on two phase qubits in binary. So all we can do is read the binary values on these phase qubits and just rotate the auxiliary qubits so that it will induce this inverse of lambda. It will induce the amplitude to C over lambda here. This is just sheer calculations. So we just decide, we just set this number of C to 1. And if the first phase qubit was 1, then we will rotate pi, the amount of pi's, angle pi. So in the case of 1, 0, it will rotate pi over 3. So, and finally, the uncompute the unnecessary qubits to get the proper measurement result. And this is the simulation result. If you only consider the ancillary qubit is 1 here, and the probability of the measuring these two states are approximately as ratio of 1 to 9 is the probability. So if it means that the amplitude, the ratio of amplitude is 1 to 3, which is same with the exact solution. So this is the HHR algorithm can solve the linear the system of linear equations. So far we have covered about the HHR algorithm. Do you have any questions?
Yes. What about our ratios?
What one ratio?
Probabilities of 1 over probability of 1 0, for example.
1 0 here?
No, not 0, 1 0.
1 0 here?
Yeah.
This will be regarded, this will be discarded, because we, in this here, this is the ancillary qubit, and the only ancillary qubit one, in the case of the ancillary qubit one, has varied amplitude here. If you start to consider the zero ancillary qubit, zero ancillary qubit doesn't have the some varied amplitude value.
For classical, it calculates projects and modify the elements of matrix. But for quantum computer, the matrix to be Hermitian. So I think it is hard to modify some specific elements of matrix.
First of all, there's a tool that we can make any of the matrix to Hermitian form, right? And I think this algorithm is a little bit different to calculating the gradient, because it doesn't. I'll explain later, but it's not calculating the gradients. So, so I can give a different answer about your question, but at least the Hermitian, some limitation of Hermitian is in theoretical level. You don't have to worry about it. So let's move on to classification. And it's basically it's just a sequential execution of HHR algorithm and Hadamard test. By computing, you can compute model variables for training, and it will be achieved by HHR algorithm, and testing model is accomplished by Hadamard test. So this is the risk scale. Is some mathematics about what we use in this SVM models. But sorry, I will skip this because this topic itself takes almost 10 minutes to explain. And to be honest, I don't have full understanding about these topics. If you have interest, you may refer some textbooks and research papers related to complex optimization. So, but all you have to remember is this is the original problem. Minimize this cost function, and final, and at the end, the problem can be reduced to this simple problem of the system of linear equations. And as you expected, we can apply HHR algorithm here. So the whole step of classification algorithm as follows. First, the system solve the system of linear equations, and second, test the model by using this test function. This time again, I will give you some example case. This is the this is from the MNIST data set, which contains the handwritten this data. So 1 to 9. In this case, I will only use 6 and 9 data for simplicity. And again, so we can't use the raw image of the MNIST data set. So we will preprocess the handwritten image data to number of pixels ratio. I mean, we just counting the pixels of each area, left half and right half, and just calculate its ratio and use them to attributes of the training data and test data. So this is the result. We have 2 training data for this example and 8 test data. And we will also assume that b equals to 0 for simplicity. I think this is a rigid assumption because we already have 2 training data. So we don't need to strictly more dimensions on this thing. So the whole process of the classification is simplified as follows. You may compare with this original process, which is written on right top here. So B alpha vector is just only have alpha here, and the inverse of matrix A has the so B is now 0, so it doesn't have to be calculated. So some here I just call it his dummy row and dummy column. So his dummy row and dummy columns are discarded, and also the 0 will be discarded here. So the first step is simplified as follows, and the also test function will be simplified as follows. So this is the full circuit of the quantum SVM. This is from here to here is just a HHR algorithm to calculate the alpha value, and from here to here is the classification part, which is this classification part. So this is the HHR algorithm. So since I explained this before, we'll skip this. And here we have new parts is for the classification. This classification circuit consists with these 2 parts. The first part is training data oracle, and second part, I'll just call it the unitary UX0. So what these circuits do is calculate this function value of this function value. So, but how can we calculate this value by using quantum computers? The authors of these papers suggested that we first build those 2 quantum states, U and V, and do some inner products between those 2. If you do mental arithmetic now, you'll easily see that this inner products of these 2 states reproduce this calculation completely. So this is the first part of the classification is training data oracle. Or what the circuit do is simply just see this, just change states of the red qubit here to x0 and x1. These qubits are from the attributes value from the training data properties, so it's directly implemented by rotation y gates, which rotate like only these values. So the end of this training data oracle, we will have states U here, which is defined on last slide here. This part is a little bit tricky because these parts, it doesn't directly define or just induce the quantum states V. Instead, they just define some unitary operator that sends V states to 0, 0. I mean, we don't have inputs as an input of this circuit as a V, so this sounds a little bit strange. You have seen this equation, this form first, but the point is the goal of this circuit is making this state. I mean, you will see these two equations are equivalent because if you multiply U x0 dagger on both sides in these equations and get the form of the adjoints of these equations will give you this. So the point is that if we do some quantum mechanical calculation, and if we have any chance to make this form of the states, I mean, or just measurements value, then we may calculate the inner product of V and U. To be honest, I'm not fully explained about this mechanism properly, but you will see this will be possible soon. So how the test data here is test data will be calculated in the same fashion we covered in training data oracle process. So at the end of the classification, we will get this quantum state. What we're going to do is apply Hadamard gate on ancillary qubit. And as you can see, it changes to ancillary qubit to plus states and minus states. And naively speaking, it starts to mix each quantum states like this. So if we measure only if the quantum states of the ancillary qubit is 1 like this, and if you just expand all of the quantum states of the psi here, and you get this expression, and at the end you will get this form which we want to find it. So it is same with the 1/2 minus 1/2 times inner product of V and U. And at the end, the probability of ancillary qubit is 1 is as follows, and you can conclude that we can calculate this test function by calculating this expression. So you will see that this is the simulation result of the measuring ancillary qubit. If the probability of ancillary qubit 1 is less than 1/2, it means the classification result is 6 and otherwise is 9. So if you compare with this training data, test data, and this simulation result, you'll see that the classification is doing its job successfully. So this is the end of my presentation. Okay, thank you for listening. Okay. Yeah.
Is it possible to classify other than words, not 6 and 9? So pre-processing was too simple. Calculating HR and HR. So maybe obviously there are more pixels left side and downside for 6 and more like pixels offside and right side for 9. So maybe, I think it's not general. So maybe I think it's hard to classify other numbers, not 6 and 9.
I think the other of these papers doesn't mention about the some scalability of expansibility of the attributes of properties, but I think it is possible because it's a matter of the how we pre-process the original data and the number of the properties. So yes, if we have more qubits to contain those properties and then it's possible to contain some other attributes in unitary. Yeah. Yeah. Yeah, just paper level is also more better than the classical algorithm. But sorry, I didn't see how actually the complexity level is decreased too. Yeah.
In the result, construct all the measurement statistics, right? So if you all numbers, you can just we all the like finally construct all the measurement statistics of
this is I didn't mention about the okay, this is just a demonstration example. I mean this only in practical level we usually don't measure this at this level because this kind of measurements means that we already do learn the same algorithm by quantum complex problem many times, so it will destroy the performance supremacy compared to classical algorithm. So what practically the HHI algorithm do is we just keep the data quantum state X in the middle of the circuit and do some other job like Hadamard test or sweat test. So in normal case, we usually don't measure the quantum states of the binary results like this.
That's the algorithm. Some cases that could be more complicated. I think it is important to calculate contains
no, yeah, because this pre-processing is only done in classical levels, so I think they didn't consider about the process itself. Yeah.
question.
Yeah.
The whole process.
Mm-hmm.
Is it more if you
so in my understanding, the bottom the classification in a classification algorithm, the one of the I would say just the bottleneck. The bottleneck algorithm of the entire algorithm is gradients, or just solving the system of linear equations. So, and solving linear equation only takes time complexity O(n). So if we improve the conjugate gradient method and the entire algorithm will be entire performance of the entire algorithm will be improved, as I know. Yeah.
Another question. How does learning happen? Do you update?
No. This quantum SVM is sort of one-shot algorithm. So if you do just calculation on HHR algorithm and build the firm and solid alpha 0 and alpha 1 quantum states to classification circuit as an input. You have yeah. Yeah. So okay. So this paper here, they did actually to run this quantum circuit in actual IBM Qiskit 5-qubit physical quantum computer, and it only get correct answer. The 60, as I remember correctly, is 64% of these test data, and they tried to improve the probability of getting the right answer, but the result was not so impressive. They only improved 3% of the yeah. This one, I didn't. I mean, I couldn't understand for the implementation physical realization of the NMR, but somehow they made the 100% some 100% get the 100% right answer. But I think they build some physical equipments in laboratory level, and no, sorry, but they got the right answer. Yes, they only mentioned about the implementation, and the time complexity only mentioned in this Cesroid's paper.